Welcome back. Today we want to look at a special case. Euclidean space as the ambient space and closed convex surfaces moving by mean curvature. And we want to show that in that case, all the surfaces contract to a point, becoming more and more round. It's an old result, 1984 or so, but it's a technique to prove it has been used over and over again in getting more and more detailed information on other singularities of the flow. So I think it's worthwhile to explain this result and the technique leading to it. So consider F a map of a hypersurface Rn plus 1 with the standard metric, smooth closed hypersurface. Call this F0, this is the initial hypersurface, and Mn0 is the image of F0 of Mn. It's convex. And we assume, for simplicity, it's uniformly convex. In other words, assume that all the principal curvatures are bounded below are positive, strictly positive. Hypersurface, and then we want to prove that the theorem, if n is greater or equal than 2, so if we have at least 2 dimensions, then mean curvature flow, which is GDT F equals mean curvature vector with initial data as a unique smooth solution on some time interval 0 up to t, which is positive but finite, and as t tends to capital T, Mn t converges to some point P naught in Rn plus 1. Only, and if we rescale surfaces Mn tilde of the rescaled around the point P0 of area or fixed volume converge to a sphere. Round sphere. Okay. So, in other words, even though you start maybe with something extremely elongated, as long as it's strictly convex, after some time, it will become more round and converge to a point. And if you rescale around here, then you get the image of a shrinking round sphere, and then if you rescale and fix, you get a round sphere. Now, in some sense, this result at the time was inspired by the work of Richard Hamilton on the Ricci flow. So remark, inspired by, let me just check here, inspired by Ricci flow, Richard Hamilton, 1982, where he looked at dt of the metric on an abstract Riemannian manifold moving in direction of the Ricci curvature of the metric. And he showed that if n is equal to 3 and Ricci of the initial metric is positive, then the solution exists on some time interval just like above, and these scalings converge to constant curvature metric. So the assumption of a positive second fundamental form is replaced by the assumption of positive Ricci tensor, and then you get the same picture. The metric becomes round as it shrinks to length 0, and rescalings converge to a constant positive curvature metric. That's remark number one. The second remark is that in this paper here, in this result, we could assume just weak convexity, and then the strong maximum principle would imply that after a short moment, the surface is strongly convex, and then the result applies. So in the theorem, weak convexity is enough, since then M and T is convex, is strictly convex for all T greater than 0. So you could then apply this theorem to the initial surface for some slightly positive time. And this means in particular that you cannot construct a counterexample to the theorem above by taking a huge long cylinder and attaching some caps at the end. This cylinder, even though it's initially only weakly convex, will immediately become strictly convex, look like this surface up here, and then the theorem applies. Okay, so how to prove this result? Well, there are several steps. One has to first show that the convexity assumption is preserved. In other words, you stay in the same class of surfaces. In the second step, you have to then show that something improves. And finally, you have to show that it improves so much that as you approach the singularity, that indeed everything gets round, and you have to prove this convergence to a round sphere. So proof strategy show convexity preserved. Secondly, you prove a so-called pinching estimate for lambda 1 up to lambda n. You want to show the principal curvatures come close together if the curvature tends to infinity. And you want to then show that if this happens, that this happens in the whole neighborhood. So you need a gradient estimate for curvature. And finally, once you have all that, you want roundness where the mean curvature blows up. Remember, if something goes wrong, the curvature has to blow up. We proved that in the last lecture, right? The only thing that something can go wrong is if the curvature blows up. And since we are in the convex case, where the full second fundamental form is of course controlled by the sum of the principal curvatures, it must mean that the mean curvature tends to infinity. So we have to show that the surfaces become round, whatever that means, as the mean curvature tends to infinity. And finally, we have to show convergence to a round sphere in some norms. Now, let's start with step 1, convexity. Convexity is preserved, so note the evolution equations. First, we had ddt of the mean curvature for mean curvature flow was Laplacian of mean curvature plus the second fundamental form squared times the mean curvature. So this means in particular by the parabolic maximum principle, it shows that if h is greater than 0, this is preserved. So since we are starting with convexity, we certainly have positive mean curvature, and this positive mean curvature is preserved by the parabolic maximum principle because h appears as a factor here in this evolution equation. If you want to look up the maximum principle that applies in this setting, I recommend to view the lecture that I gave on Ricci flow, how the maximum principle is applied there. It applies in exactly the same way here. So we have positive mean curvature. Now, so this is the easy thing. So the second thing you notice that if we have positive principal curvatures, then mean curvature is strictly positive initially, so there must be some lower bound because it's a compact surface. So Mn0 compact, h greater than 0, implies that the minimum of h on the initial surface is equal to some h0 is positive. But then you can compare this evolution equation here with the corresponding ODE. Then note that ddt of h is bigger than the Laplacian of h, and here a squared is bigger than 1 on n h squared, so this is bigger than 1 on n h cubed. And then we can compare with the ODE solution ddt of phi equals 1 over n phi cubed. and we conclude that, in fact, that the mean curvature minimum on the surface at time t must be bigger than some constant c1 divided by square root of some constant c2 minus t. And this, in particular, this right, and you can compute C1 in terms C1 and C2 are constants of n and h0, C2 and h0. I leave this as an exercise. So you get a lower bound that tells you in particular that t approaches, as t approaches this constant C2, that then the mean curvature has to tend to infinity, so the solution can exist at most up to time C2. And actually, the C2 is some C2 tilde depending just on n times h0 to the minus 2. So this lower bound on the mean curvature tells you a upper bound until a smooth solution can exist at most. So we already have our first a priori estimate. We know that given a convex initial hypersurface, there must be some upper bound on the existence of a smooth solution. We know exactly when a first singularity has to occur at the latest, namely at this time here, given by the solution of this ODE. Okay, so we have positive mean curvature. Now we want to show that convexity is preserved. Now, for that, we need the evolution equation of the second fundamental form. So, for convexity, we use the evolution equation for the Weingarten map. And we had shown that this is equal to Laplacian of this Weingarten map plus a squared times the Weingarten map in Euclidean space. This was the evolution equation. And the eigenvalues of this mapping are exactly lambda 1 up to lambda n. So we have to argue that if the eigenvalues of this matrix are positive, then they remain positive. But this is exactly the statement of the maximum principle of Richard Hamilton. So the maximum principle of tensors, again, this is explained in the lecture in my Ritchie flow course, which is online. Maximum principle for tensors by Hamilton says that this is Hij positive is preserved by the flow, provided the right-hand side tensor, which is a squared times Hij, is non-negative on the boundary of this set. on the boundary of the set of lambda where lambda I is positive. But of course, on the boundary, if I have a matrix with a zero eigenvalue, then this matrix, which is just a multiple of this one, this has also a zero eigenvalue. So this is clearly satisfied. So convexity, so lambda I greater 0 for all I is preserved. So we have convexity preserved just by a direct application of Hamilton's maximum principle for tensors. But we can even do better. Namely, if the thing is strictly convex and the mean curvature is convex, it must be true that initially each principal curvature is bigger than some fixed fraction of the mean curvature since the manifold is compact. So Mn0 compact and H greater 0 and lambda I greater than 0 must mean that there exists some epsilon bigger than 0 such that on Mn0 you have that lambda I is bigger than epsilon times the mean curvature, which is equivalent to saying that the tensor Hij divided by mean curvature, let's call this Mij, is positive and satisfies that Mij is bigger than epsilon times delta Ij. Okay. Now, let's apply the maximum principle to this tensor Mij. By tensor maximum principle. Okay, if we do that, we have to compute the evolution equation of this tensor. So compute ddt Mij is equal to ddt Hij over h minus Hij over h squared times ddt h. And then you see this is equal to Laplacian of Hij over h minus Hij times Laplacian of h over h squared. These are the leading terms coming from the Laplacian here and the Laplacian there. But the absolute terms just cancel out perfectly because this is a squared times h divided by h gives a squared Hij, and the same here, this gives an h times a squared, so the absolute terms cancel out completely, so this is all we get. On the other hand, we can also compute Laplacian. The idea is always compute the Laplacian of whatever you need to compute, right? So because the Laplacian is a natural operator associated to mean curvature flow, makes sense to compute the Laplacian of this thing and compare it to the right-hand side. So we take the Laplacian, this is a gradient k hij over h minus hij over h squared gradient kh, which is equal to Laplacian of hij over h from here, and then from here we get minus hij over h squared Laplacian h, which is this term. But then we have some more terms. We get from here a minus gradient k hij over h squared gradient kh. And then from here we get exactly the same term again, so we get two of those. And then we still get the derivative of this one here. So this is plus 2 on h cubed hij multiplied with gradient h squared. And now notice these last two terms here, however, can be combined to be just that's just this term multiplied by 2 over h times gradient of k. So this is the same as minus 2 gradient k of h over h times the gradient k of hij over h. So we end up the fact that ddt of mij is equal to the Laplacian of mij, which is this term here, minus 2 gradient kh over h times gradient k of h of mij. And now this is just a vector field times the gradient of this. And Hamilton's maximum principle applies to this situation. So this thing here is not perturbing the maximum principle. So the inequality with respect to a constant right-hand side here, both from above and below actually, is preserved. So this implies, by the maximum principle of Hamilton, that an inequality of the type hij over h bigger than epsilon times delta ij, and actually also less than beta times delta ij, is preserved. So we have this uniform, rather than just proving that convexity is preserved, we have been able to use the maximum principle to show that the maximum principle shows you a uniform control on the second fundamental form, which is scaling invariant. Notice that this quotient here, the quotient of the principal curvatures by the mean curvature, is a scaling invariant quantity. So we found something that is preserved, some control that even survives any kind of rescaling that may want to do in the future. We've proved a scaling invariant property of the surface that is preserved. We have uniform convexity in a scaling invariant way that is preserved with a fixed epsilon and a fixed beta for all the time where the solution exists. It just depends on the initial data and with a fixed epsilon and a fixed beta for all the time. Okay. So that completes the first step in the proof to show that the surfaces remain as nice as they started in a precise quantitative way. And we know that something has to go wrong in finite time, and we have an upper bound on this finite time in terms of the lower bound on the mean curvature on the initial surface. You could, of course, also have found another criterion. Since the thing is compact, it must be contained in some big ball, and that big ball is a barrier and it will die in a finite time. So you could have also obtained an upper bound on the time of existence in terms of the diameter of the initial surface in Rn+1. I leave that as an exercise. So the second step now is that we want to prove a pinching estimate on the eigenvalues lambda 1 up to lambda n. In essence, we want to show that these eigenvalues come closer together if somewhere the mean curvature goes to infinity. So for that, consider the following quantity. So a motivation we have that a squared is bigger than 1 on nh squared. This is true for any matrix. And in fact, this is the difference, a squared minus 1 on n h squared. This is, you can write this as the sum, let me see if I get the constants right. Yes, this turns out to be just 1 over n times the sum of all the pairs of principal curvatures, the difference is squared. Another way of seeing it is, so it is equal to 0 if and only if all the principal curvatures are the same. So, so this quantity measures how far, that measures the roundness at the lambda level at each point. Another way of looking at it is if we write A0 for the trace-free part of the second fundamental form. So this is the trace-free part, and H0ij is equal to Hij minus 1 on n H times Gij. Then you see that A0 squared, so this tensor is clearly equal to 0 if all the principal curvatures are the same, namely equal to 1 over n times h, then this would be exactly 0. Now, if you compute the norm of this trace-free part of the second fundamental form, you get, of course, a squared from the first term. Then you get from the term at the back, you get a plus 1 on n squared, h squared times n, since the square of the metric is n. And from the cross term, you get minus 2 over n times h times the trace of hij, which is h. So we get minus 2n over h squared. So this is equal to a squared minus 1 on n h squared. So you can also see this quantity as the trace-free part of the second fundamental form squared. And what we want is a upper bound on this quantity. And the theorem we want to prove is that given Mn0 contained in Rn plus 1 and greater or equal than 2, and with Hij bigger than epsilon times H delta Ij, so uniformly convex, there are constants sigma greater than 0 and C1 less than infinity, depending on the initial surface, in particular its area, on the epsilon and on n, such that it is true that this trace-free part of the second fundamental form is less than this constant times h to the 2 minus sigma on Mn across the whole time interval where a smooth solution exists. Now, why is this so significant? Well, I could reformulate this. I could also write it like trace-free part squared divided by h squared. Right? This is the left-hand side. The trace-free part divided by h squared is less than a constant times h to the minus sigma, because the minus sigma remains after dividing by h squared. And this quantity here, of course, decreases to 0 as h tends to infinity. So we've shown that the scaling invariant quantity that measures how round the surface is at any point, the scaling invariant quantity tends to 0 if we approach a singularity where h must go to infinity, as we know from the last lecture. So this estimate sort of says at the curvature level, wherever the mean curvature tends to infinity, the surface at the curvature level looks like a round sphere. This is still not enough. We have to show that the whole surface everywhere then has mean curvature tending to infinity if it somewhere goes to infinity. But this estimate is the first major breakthrough saying that the surface gets nicer as it contracts towards higher curvature regions. The principal curvatures of this convex surface come together. And of course, this estimate is only true since we have our pitching estimate. It heavily depends on this constant epsilon exploiting the convexity. So that's the estimate we want to prove. And it turns out that this estimate cannot just be proven by the maximum principle. There's a similar estimate in Ricci flow that Richard Hamilton proved when showing that in 3 dimensions, metrics of positive Ricci curvature become round at the end of Ricci flow. And he proved such an estimate for the principal curvatures for the eigenvalues of the Ricci tensor. And he could do that just with the maximum principle, with a slightly more algebraically involved argument than we just used for the preservation of uniform convexity. But it was just the maximum principle, just analyzing the algebra of the reaction term in the evolution equation of the Ricci tensor. Here, we do not get away with the maximum principle. And that has to do with the fact that in the evolution equation of this quotient, remember we were looking at hij over h, so the evolution equation of this quotient has no reaction term left. So the reaction term does not improve this quotient at all. This is different in Ricci flow. So that this equation here is the main difference to Ricci flow. In other words, there's no improvement whatsoever coming from this gradient term and from the reaction term. There is no reaction term. So any kind of improvement must come from the Laplacian, must come from the smoothing properties of the Laplace operator in this equation, rather than from the maximum principle. So to prove this, we will have to exploit the diffusion operator. And the only way to exploit that is with the help of integral estimates. So we have to prove this theorem here with integral estimates. So we will have to use the tools will be the Sobolev inequality and Stampacchia iteration, starting from LP estimates on suitable quantities. Okay, so let's start on that technique, which turns out to be important, not just for this result, but for many results later on the classification of singularities. But again, I start from this quantity, from this evolution equation here. Right, so so note that if Mij is equal to Hij over H, then we get that Mij squared is just A squared over H squared, right? Because this is the second fundamental form. So from here, we immediately get that ddt of the quotient of A squared over H squared is equal to twice Mij Laplacian Mij minus 4 gradient kh over h gradient k Mij times Mij. But this one here is, you can clearly write this as the Laplacian of Mij squared. Oops, what did I write here? Yeah. Laplacian of Mij squared. And then the mistake I made is the Bochner term, so it's minus 2 times the gradient of Mij squared. This takes care of this term here. And then here, notice that twice the gradient of this is the gradient of Mij squared. So I can write this as minus 2 gradient kh over h times the gradient of so I just took this from here. So we get, so let's write it together. We get ddt of a squared over h squared, by the way, which is of course, since 1 on n h squared divided by h squared is a constant, I can just as well write it like this. So this is ddt of the trace free part squared divided by h squared. And this is, let's write it out, this is a Laplacian of, for the same reasons, I can write this here. I can, because of this is just a constant, I can switch between these two things, minus 2, and here we get the gradient of a squared over, gradient of mij. Yeah, let's write a k here, so you see all these terms that we get this thing here, minus 2 gradient kh over h gradient k a0 squared over h squared. Okay, so this is the evolution equation of this constant. And the first thing, either by writing a0 squared here or a squared, which in this case is the same thing, we see this is, of course, just the gradient of the same quantity, and this is a negative term. So we immediately see something very simple. We see proposition. And notice this has nothing to do with convexity. The simple proposition is just true already if h bigger than 0. And this computation makes sense. So if h is bigger than 0 on the initial surface, then the maximum of a squared on the surface nt is less than the maximum of the same quantity on the initial surface. Just by the parabolic maximum principle for scalar quantities, for this scalar quantities. See, there's just a negative term and something linear in the gradient, so we must have this constant. So there must be some constant c, depending just on the initial data, let's call it C1, such that a squared is completely controlled by the mean curvature. So the statement that I said before, if it is convex and the curvature goes to infinity, it must mean the mean curvature goes to infinity, gets a very quantitative setting here. It is true that any time for a fixed constant, just depending on the initial data, the second fundamental form squared is uniformly bounded by the mean curvature squared. Okay, so in other words, the mean curvature controls everything. And it controls the scale of the blow up of curvature if curvature goes to infinity, because of course a squared is bounded below by 1 on n times h squared. So a squared and h squared in terms of size are completely equivalent. Now, what we want to show, however, is that this trace-free part is much smaller than the mean curvature. So we want to get this quantity actually small, and the trick will be to squeeze in this extra power sigma in here, and that slightly changes the evolution equation. I leave the computation to you, but just now multiply this thing, this quantity, by h to the sigma, where sigma is some positive number. So now break the scaling by making the quantity larger in terms of curvature by multiplying a squared trace-free part with h to the sigma or some sigma positive, and call the resulting quantity f sigma. Let f sigma be the trace-free part divided by h to the 2 minus sigma. This is a squared minus 1 on nh squared divided by h to the 2 minus sigma, and sigma is a positive number. And then use the evolution equation for h, which is Laplacian h plus h a squared, and well, use the quotient rule, do some computation, compute, and you end up with that ddt of f sigma turns out to be Laplacian of f sigma plus 2 times 1 minus sigma divided by h times a gradient kh, gradient k of f sigma. That is, oops, did I get? I must have gotten, let's see, did I have a sign error somewhere? Just check. No, I don't think so. Maybe. No, it's correct. Minus 2 on h to the 4 minus 4 minus sigma times h gradient I hkj minus gradient I hkj. Yes, squared, and then minus 1 minus sigma times sigma divided by h to the 4 minus sigma times a0 squared times gradient h squared. And then there is one extra term, which is plus sigma a squared f sigma. Okay. So, by the way, here in this computation, note this term here comes from this square here. Right? So the term gradient gradient I of mjk squared, this is the gradient of I hjk over h minus hjk over h squared times gradient I h, and when you square this, you get a 1 on h to the 4 times h gradient I hjk minus hjk gradient I h squared. So this square here is exactly coming from the square we had in this evolution equation up here. And this term, of course, comes from this term here. And the extra term involving the factor sigma here and here comes from the multiplication with the term h to the sigma. Now, let's see, how did the equation improve compared to the case sigma equals 0? Obviously, this agrees in case sigma equals 0 with the equation we had before. This one didn't change much. It's still linear in the gradient of f sigma, so it does not hurt us. The negative term here is still there. It just has a slightly different power of h here. So we still have this good term. And this term here, since sigma is small, this has the right sign. So this whole thing here is negative because of the minus sign. So we can throw it away. We will just ignore this term. And the real change compared to the previous equation is this term here, sigma a squared f sigma. And that's a really bad term because if the a squared wasn't there, this would be just exponential growth of f sigma. And since our time interval is finite, this term cannot hurt us. But the a squared in front of it is really a disaster in the sense that we know near a singularity a squared is going to blow up. So potentially this is causing trouble and cannot be controlled. The only hope would be that we have a small factor sigma in front of it. So maybe if the sigma is very small, it can be absorbed somewhere. Now, there is no other absolute term. So there's no way to absorb it with the maximum principle as was possible in the Ricci flow. In the Ricci flow, there was another good term floating around coming from positive Ricci curvature. And you could absorb this term. And if sigma was small, and you could then prove the pinching estimate just by the maximum principle. But here, the only good term you have is this one here, it has a sign, and the diffusion term, the Laplace. Now, to exploit the diffusion term, you need integral estimates. So the only chance to really exploit this good term here in order to absorb this and combine it somehow with the good term from the diffusion term here would be integral estimates. So the idea is to use this good term here. So this is a good term. And this one here is the good term. And this one here is the bad term. Okay. Right. So before we go to the integral estimates, let me show you how good this term here is, because it may not be good in general. For example, we know this term comes from this term here. But this quotient here is really, yeah, I didn't write this right. This is not MIJ, this is HIJ, sorry. This is HIJ. So this term here, say, on a sphere, Hij over H is always 1 on n. or on a cylinder, it's 1 over m minus n, depending on what your dimension of the cylinder is. So on a cylinder and on a sphere, this quotient here is constant tensor, just a multiple of the identity. So its gradient is 0. So this term here is vanishing on cylinders and on spheres. Now, on the other hand, if we are on the sphere, we are home. There's nothing to be proved. So somehow we have to exploit this term, argue that this is a good term in case we are not yet on the sphere. So the exploitation of this term is not completely trivial, okay? So we need a little lemma telling us that this term is a good term in case we are on the, in case we are not on the sphere. And this is the following lemma. Let's go with lemma 1. So suppose Mn contained in Rn plus 1 and greater or equal than 2 is a hypersurface with positive mean curvature and second fundamental form bigger than epsilon times the mean curvature times G, which of course is equivalent to saying that all the principal curvatures are at least a fraction of h for all I equals 1. Then, this has nothing to do with evolution equations, just a fact about uniformly convex hypersurfaces. Then it is true that this tensor is bounded from below by 1/2 epsilon squared times the second fundamental form squared or mean curvature squared times the gradient of the mean curvature squared. And actually, I can leave it for you as a little exercise. Show that even right-hand side, how that right-hand side can even be replaced by some other constant depending on n and epsilon times the mean curvature squared times the full gradient of the second fundamental form squared. You can have on the right hand side, you can not just get the mean curvature, you get the full gradient of the second fundamental form. So this estimate is of course meaningless if you're on the sphere or on a cylinder, because then the right hand side is 0. So in this sense, it's an estimate that is only valid, valuable in case you are on a hypersurface which is not yet spherical or cylindrical. So for the proof, the key idea is to consider the irreducible components of this tensor. Whenever you have a tensor with more than one index, it's always useful to decompose into the irreducible components to get sort of optimal inequalities. And the simplest case would be that the square of a matrix is bigger than 1 on n times the mean curvature squared, where you just decompose into the trace-free part and the trace part of the matrix. There's a general theorem that you get the, going back to Y, that you get all the irreducible components, but either taking traces or by looking at symmetries and antisymmetries. So here we want to exploit the fact that the term on the left here, gradient IHJK, by the Kodazzi equations is totally symmetric. So the antisymmetric part of this vanishes. So if we decompose this into the symmetric and antisymmetric part, we only get this term involving the mean curvature. So by decomposing into symmetric and antisymmetric part using Kodazzi, which says that gradient IHJK is totally symmetric, there's no antisymmetric part, I get that the left-hand side in this inequality is bounded below by, so antisymmetric part of this thing, you take 1/2 of this and its antisymmetric part, square it, so you get 1/4 of the norm of gradient IHJK, and to antisymmetrize it, say in I and J, you get gradient JHHIK squared. Now, unless the gradient H is 0, when this inequality is true anyway, we can pick a direction in which gradient H is pointing. So suppose gradient H is different from 0 and set E1 to be the direction of the gradient of H. Then I get that the left-hand side is bounded from below by those terms where I is equal to the components. I only have to take those components where, and then I have here, taking the square of this, I get gradient H squared from both sides, and then from here I get A squared, squaring this, and sum over, and then from here I get another A squared, but then the cross term gives me -2, and then I is equal to 1, and J must be equal to 1. So I get, I only get something is I, if I equals 1 and J is equal to 1. So I get H1K squared, and the sum over all the K from 1 to 2. 1 to n, sorry. Okay. So the 2 cancels with the 4, give me 1/2 gradient H squared. And then here, let's see what's left. Now, A squared is the sum of all these squares. Now, it has the H11 term cancels exactly with the H11 term here, but then A squared, all the ones that have a K appear twice, so we get the sum of k equals 2 to n of h1k squared. This is left, and the other one that is left is all the terms sum of j and k greater or equal than 2 up to n of hjk squared. And now I'm exploiting the fact that the dimension is at least 2. In dimension 1, of course, I don't get anything because this term is not there and this term is not there, and I have nothing. That's why this whole theorem only works from n at least equal to 2. So if n equals 2, then we have this term here, I throw it away, but there is one term left, and that is h2 squared at least. So if you like, you can put, you have at least diagonal terms, n minus 1 diagonal terms. In each one of the diagonal terms is bigger than the smallest eigenvalue. The smallest eigenvalue was epsilon times h because of our convexity estimate. So this must be bigger than 1/2 actually times n minus 1 times gradient h squared times epsilon squared times h squared. And this proves the result since n is greater than 2. Okay. So we can conclude that ddt of this quantity f sigma is less than Laplacian of f sigma plus 2 times 1 minus sigma divided by h gradient kh times gradient k f sigma minus and this was there was a 2 there, right? So we just get epsilon squared times h to the 2 minus sigma times gradient h squared from this good term, and then we had this terrible term sigma a squared f sigma. Okay, this is the inequality we end up with. Just check that I got it right. Yes. Okay. Now, the issue now is how do we get a upper bound on this? Obviously, we're only going to get it in terms of an integral estimate. Now, let's see. You may just have still time to do that. The first thing one has to prove is a Poincaré type inequality, which estimates p norms of this term in terms of gradients of h squared multiplied with lower norms of f sigma and gradient of f sigma squared terms. In other words, we want to absorb a curvature terms in a higher order gradient terms, which is some kind of Poincaré inequality. Now, this Poincaré inequality is explained in more detail in the tutorial, but let me just give you to make the lecture self-contained, let me give you the main idea, the philosophy behind. So the key here is the commutator identity. So use commutator identity for a second fundamental form, or for the second derivatives A, which is also known as the Simon's identity. James Simons. And this was done before we needed in deriving the evolution equations. We had seen that the Laplacian of the second fundamental form, the trace of the second derivatives, is the same as the derivatives of the trace. And then there was minus a squared times the second fundamental form plus h times the square of the second fundamental form. Now, and then multiplying this by the second fundamental form, you get that Laplacian of the second fundamental form is, on the one hand, the Bochner term that you always get when you do such Laplacian of a square, when the derivatives fall on the factors, one each. And on the other hand, you get twice this term. So we get twice hij, gradient I, gradient jh, minus 2 times a to the 4th, and plus 2 times h times the trace of a cubed. Okay. You see now, and now we have gradient terms, 3 gradient terms in the equation, and we have 2 absolute terms. Now the point is that in case we are convex, these terms have a sum. So let's call this term here z. So let z be h times trace a cubed minus a to the 4th. And then we get another lemma exploiting convexity, saying that this z is bounded below by n, so lemma 2. If on any hypersurface we have that lambda I bigger epsilon than h, or I, then we get that z is bigger than n epsilon squared times h squared times the trace b part of the second fundamental form. And the proof is quite simple. It's just algebra. We write z as the sum over I of the lambda I times the sum over j of the lambda j squared, lambda j cubed, sorry, minus the sum of the lambda I squared, and multiply that with the sum of lambda j squared. And now symmetrize this in terms of lambda I and lambda j. This is symmetric already, but here we could have also written sum of lambda j times the sum of the lambda I squared. If I put that all together, I get the sum over I and j of the 1/2 lambda I squared plus 1/2 lambda j squared. That's this term, and then minus lambda I squared lambda j squared. And now you see that we can take a lambda I, lambda j out of everything. And we get 1/2 lambda I, 1/2 lambda I, lambda j, and then the others complete the square. And then if I just, since this is over all pairs I and j, so I only take the ones where I is less than j, then I can get rid of the 1/2 and I get this. And now you just insert here, for the first two terms, you insert the epsilon squared, h squared, and recall that sum of all the differences of the squares was n times the trace free part of the second fundamental form squared, and we get the result. This is the lemma. And now notice that this term here, the z, this is the thing that came up in our f sigma, right? So this here, this can be rewritten as n times epsilon squared times dividing by h to the 2 minus sigma, multiplying by h to the 2 minus sigma gives an h to the 4 minus sigma times f sigma. So the term on the right-hand side here is exactly related to our function f sigma, which means that now going back to our evolution equation, it means that we can estimate the bad term in our equation. We recall a squared is comparable to h squared. So we can compare this bad term, if we multiply it with the right things and integrate, we can estimate integrals of powers of f sigma in terms of gradient terms. So in the first step, one has to use now, so recall, take note of this equation, and now in the first step, one has to take the Simon's identity star and multiply it with the right thing to get the following proposition. And this proposition says that let p be greater or equal than 2, and then for any eta positive and any non-negative sigma less than 1/2, it is true that n times epsilon squared integral f sigma to the power p times h squared d mu over the surface is, yeah, of course, I need the uniform convexity, of course, in order to apply lemma 2. So this can be estimated by 2 eta times p plus 5 times the integral of 1 over h to the 2 minus sigma times f sigma to the p minus 1 times gradient h squared. That's coming from integrating gradient h. And the other term is eta to the minus 1 times p minus 1 times integral f sigma to the p minus 2 gradient f sigma squared d. And the key idea is to take this Simon's identity and proof idea multiply star with, and you see what you need here, you have one power of f sigma at the moment. On the right, you want f sigma to the p, so you have to multiply by f sigma to the p minus 1. And on the other hand, you want a h squared, so you have to multiply with a 1 over h to the 2 minus sigma, and then you have the right power, and you just integrate. Okay? And then the thing you have to notice that the term here, this is 2 times z, and this is 2 times gradient a squared. And they have the same sign, so they're both good terms. Note that 2 times z plus 2 times gradient a squared yield good terms. Integrate by parts. To eliminate all second derivatives of curvature, right? So there's a second derivatives of h, which you get rid of by an integration by parts. And there is the Laplacian, of course, which you also estimate by an integration by parts. And you can always estimate gradient a, mod a divided by in terms of gradient a. So integrate by parts to eliminate second derivatives of curvature. And the rest is Hölder's inequality. Use the Schwarz inequality, I guess, is all you need. Okay. Well, these are the ideas, and then you end up with these things. And the important thing here is that this term here is of order linear in p times eta, and this is also linear in terms of p. So you can play with these powers, and then this will be a useful inequality in treating the bad terms in the evolution equation. Maybe I finish with the LP estimates for the F sigma. So how do we apply the Poincaré inequality? So now start use the inequality dbt F sigma is less than Laplacian of f sigma plus 2 1 minus sigma on h gradient kh gradient kf sigma minus 1 on h to the 2 minus sigma gradient h squared, and there was an epsilon squared here, I think, yeah. And then there was the bad term sigma a squared f sigma. And now we just compute what is ddt of integral of f sigma to the p d mu. This is, we want to estimate an LP norm of this quantity. And well, you just do it. You get from the area element, you get a minus h squared times f sigma to the p d mu. So from just differentiating d mu, and then you get plus p times integral f sigma to the p minus 1 times Laplacian f sigma plus 2 times 1 minus sigma on h gradient kh gradient kf sigma minus epsilon squared on h to the 2 minus sigma gradient h squared plus sigma a squared f sigma d mu. And then you see, now actually I have to tell you, this term here, first long time ago I thought I could absorb the bad term here in there. I thought, okay, here's p, I just make sigma something like that constant, you know, a squared is bounded by constant times h squared. So I take sigma like 1 over p times 1 over that constant and absorb the bad term in here and get rid of it. But that would mean that I have to make the sigma very small compared to p. I have to choose sigma like 1 over p. And that turns out not to be good enough. In the later step, when you want to turn the LP estimate into a sub-estimate, if the sigma is so small that it is like 1 over p, then as you take larger and larger p's, turns out you get nothing. If you can take the sigma slightly larger than 1 over p, here in our case, with the help of the Poincare inequality, we will see we get away with something like sigma like 1 over square root of p. Then it just works. But 1 over p is not good enough. So this term does not help. So I just throw it away. So the idea is then to estimate this by the bad term, and the bad term has the form sigma times p times integral a squared f sigma to the p d mu. This text gives us the bad term here. And then we get one good term coming from the epsilon squared times p times integral f sigma to the p minus 1 times 1 on h to the 2 minus sigma gradient h squared d mu. That's this good term here. And then you get a good term coming from integrating the Laplacian. So this gives you a term which looks like p times p minus 1 times integral f sigma to the p minus 2 gradient f sigma squared d mu. And when you look at the blackboard above, the two good terms here, the two good terms that we have down here with a minus sign are exactly the two terms on the right-hand side that allow me to estimate this term. All right, so the two good terms that I get from the evolution equation, one from the convexity that allowed us to exploit this square of gradient, so that's this term, the good term, and the other coming from the diffusion term from the Laplacian. So I have these two good terms, one coming from the convexity, the other coming from the diffusion, and they are just good enough in this Poincaré inequality to let us estimate a term like this, which is as good as our bad term here. There is still one cross term here, but this is lower order. It's easy to see. So there is still this term 2p. And here, I just brutally estimate this by absolute values times 1 on h times gradient h times gradient f sigma. And you can easily see that by the Peter-Paul inequality, this can be absorbed into those two terms with plenty to spare to absorb this bad term. In fact, you can estimate this. You can now use this and the Poincaré inequality to even have a little bit left over. So you can have something here like 1/2 sigma p with a minus sign times integral a squared f sigma p to the power p d mu. And so certainly you get something that's less or equal to 0, and you have to play, you have to see for which p's this works, provided, so you have to choose the p depending on the epsilon sufficiently large to squeeze this term linear in p into the epsilon term and the term which is quadratic in p, right? This is linear in p, this is linear in p, this is quadratic. So clearly if the p is large enough, you can squeeze it in there, and what you need is that this is bigger than 100 epsilon to the minus 2, and the sigma now has to be like something like 1 on square root of p. So you need the sigma to be less than n over 8 times epsilon cubed times p to the minus 1/2. Okay. Crucial thing here is that it only has to be like p to the minus 1/2 in order to squeeze this term, again, linear in p. You have to squeeze it into the epsilon term and into this term with the help of the Poincaré inequality, which is in this proposition. But that's just a trivial application of this inequality to this estimate. Right, so then we get the LP norm decreasing in time. And let's summarize this by just stating that we have an upper bound for the LP norm for all those p's. So as a conclusion, you get a theorem, well, let's call it a proposition, all on the way to the pinching estimate. The proposition says that provided, so suppose MNT is a solution of mean curvature flow with lambda I bigger than epsilon h, for all I equals 1 up to n. So we have a uniform convex solution. Then for p bigger than 100 epsilon to the minus 2 and sigma less than n over 8 times epsilon cubed times p to the minus 1/2, we have the LP norm at the LP norm bounded by a constant C1, which is just depending on the initial data on the whole time interval where the solution exists. Okay, we have this. We bounded this P norm for this range of P and this range of sigma. And now it remains to show that we can pass from this LP estimate to a subestimate. Now, when you try to do that, look at this evolution equation here. Suppose we try to go with the Stampacchia iteration from an LP norm to a subestimate. What will happen is that on the right-hand side, you know, we multiply with f, the maximum of f sigma minus k and 0 and some power of that. And then we get these integrals of this cutoff f sigma time, but they have this factor a squared or h squared. So we have to have those integrals bounded for some large p. But at the moment, we only have the LP norm bounded, not the higher, not integrals of the type f sigma, integral f sigma to the p times integral h squared. But that's what we need in order to go from the LP estimate to the subestimate. So somehow we need a version of this estimate with a factor h squeezed in here. And that's what we can do, provided the sigma satisfies this estimate in terms of p. It only goes down like 1 over square root of p. And I guess I leave it here, and next time I show you this, how to pass from this LP estimate for just the right range of sigma and p to an subestimate for f sigma, and that subestimate is then the pinching estimate. Thank you very much.